Okay, so welcome to this next video in the Theory of Probability playlist. So in this video we're going to continue our discussion of moment generating functions, and we're going to do our final MGF example, which is we're going to take the MGF of the Poisson distribution, so of the Poisson. Okay, so as always, this is our setup. We have some abstract probability space which has a random variable x, which is mapping it, in the case of the Poisson, onto the the non-negative integers, so 0, 1, 2, 3, 4, 5, etc. So x is Poissonly distributed with some parameter lambda, and we know that that means that the probability mass function, so the probability that x is actually equal to some little x, remember, is equal to e to the negative lambda, lambda to the power of x over x factorial. So if you like thinking about pictures, you've got 0, 1, 2, 3, 4, etc. And we are calculating this number and plotting it as a sort of discrete graph. So you don't have values in between. Well, you could imagine having values in between. It's just 0 in between. Well, actually, yeah, you can imagine having values in between, but it's just 0. The only places where it's non-zero are these specific numbers 0 to infinity. But really, it's only a mapping from that set 0, 1, 2, 3, 4, 5, 6, etc. And all of these, if you sum up all of these values, it obviously has to sum up to 1. Well, it has to converge on summing up to 1 as you sum up more and more of the terms as you go on to infinity. Okay, so if we want to calculate the moment generating function for this random variable x, so the moment generating function of the random variable x as a function of t is going to be equal to the expected value of e to the tx. So basically what we're doing is we are setting up a function which I will call t for transformation, which is going to set a map each one of these numbers onto e to the t of that number. So t is going to map some little x, which is an element of this set, so it's a non-negative integer, and it's going to map it onto e to the t of that little value of x, where t is just some constant as far as this map is concerned. But of course we're letting t equal whatever real number you like. So pick whichever real number you like for your value t, and you set up a transformation, which of course I could label this as a, it depends on your little value t. So transformation as a function of t is going to map x onto e to the t of x. So in the case of 0, no matter what t you pick, is always going to be mapped onto 1. So 0 goes onto 1. 1 is going to go on to e to the t, so fill in 1 there. 2 is going to go on to e to the 2t, and etc, etc. And then what you can view this the composition of these maps. You can view that as, let's say, another random variable y, which is the composition of these two maps, and this is also going to be a random variable because we're going to let this is a set of real numbers, and we're going to let it inherit the probability space structure of this one over here. So in other words, we're going to let the probability that y is equal to some, let's say, e to the t of some value x. So that's all the numbers in here, basically, where x... I feel like I'm conning you because I'm just using e to the t of x. So in fact, let's say y is equal to some little y rather than saying that. But we know, of course, that if basically little y is just any element in this set, and little y is always going to have the form e to the t of x, where x is some positive, well, non-negative integer. So non-negative integer. I'll just... what's the symbol for non-negative integer? I feel like if I put a plus there, it means the positive integers. So I'll put union 0. There we go. Okay, if I want the probability that y is equal to some value in here, it is just equal to the probability that x is equal to whatever little x gave rise to that y. So if y is equal to e to the t of little x, then the probability that y is actually equal to that value. So if I want the probability that y is equal to, say, e to the 2 of t, it's equal to the probability that x was equal to 2. So I'm letting this space here inherit the probability space structure of that. And once you have, we know that this is a valid PMF because, we know it's a valid PMF, i.e. all of the all of the probabilities sum to 1, well, when you sum up all of these, it's going to be exactly the same as summing up all of these. So this is going to be a valid PMF as well over here. So this is indeed going to be a valid probability space, and it's going to be isomorphic to this probability space over here. And what we want to now know is what is the expected value of this random variable y. So just to emphasize the point more, if this was a probability space homomorphism, and this is a probability space isomorphism, so we don't necessarily know that this is one-to-one. This might be mapping whole events onto a single number 0 rather than mapping a single outcome onto there. So lots of outcomes might be mapped onto a single one here. So we don't know whether it's bijective. So it might not be necessarily a probability space isomorphism, but it's certainly a probability space homomorphism. And this is a probability space isomorphism, then the composition of them is still a probability space homomorphism. So indeed, this is a random variable, basically. Okay, so the probability. So if we want to now work out the expected value of this random variable y, so the expected value of e to the tx, it's going to be the sum over every possible value that you can take on in here, but that we could just do the sum over x is equal to 0 to infinity, and those values are just e to the tx. That will cover every possible value in here, and then we just need to times it by the probability that it's equal to that value, which is just the probability that x is equal to x because of this agreement here. So that's where Lotus comes from, basically. That's just another discussion of, this is the law of the unconscious well, the law of the unconscious statistician is more general than this. It says that for any function g of big X, you can do this exact same thing. But that's the argument for why you can do that. Especially, it's very beautiful in discrete probability spaces like this. Okay, so we now know that the probability that big X is equal to X is given by this formula up here, is equal to e to the negative lambda, lambda to the x over x factorial. So let's just stick that in, and we get that this is the sum, x is equal to 0 to infinity, of e to the tx times e to the negative lambda, lambda to the x, over x factorial. Okay, so pull out the e to the negative lambda because that's just a constant, and then we can group some terms here together. We can group together e to the t, and we can times that by lambda and put all of that to the power of x divided by x factorial. The reason is that this e to the t is to the power of x and lambda is to the power of x. If we expand this out, this will go to e to the t of x times lambda to the x, basically. So that's just basic rules of exponents. Okay, and now what we need to do is, just write that more carefully, we remember that e to the, let's say y this time, e to the y, the Taylor expansion of this is the sum, x is equal to 0 to infinity, of y to the power of x over x factorial. So you might think I've written that rather odd. Usually we use the symbol x in the place of y, and we use r in the place of x. But all I've done is change the symbols there to show you how this parallels with what we've got over here. So this looks very much so like this. This looks like e to the ty, e to the t lambda, sorry, e to the t lambda. So the exponential of the thing in here, basically, this is functioning for y. So if I get my coloured pens out, this bit is equivalent to the y here. So we stick it in there like so, and we get something that might look a bit odd at first. We've got exponential of an exponential. So we're doing the exponential twice, which is something you might not have ever seen before prior to doing probability. I certainly hadn't ever seen it before. Okay, so the expected value of e to the tx is therefore, the moment generating function is this, and therefore it is equal to e to the t times lambda. So there we are. Oh, sorry, I've made one little mistake. That is this bit here, times e to the negative lambda. So we pulled out this e to the negative lambda here. So now if we put those together, we get e to the lambda e to the t minus 1 like that, and that's the more usual way that you would see it written. I thought something looked odd, and it was, yes, we've missed that. Okay, so that is the moment generating function for a random variable x which is distributed Poissonly with parameter lambda. Okay, so now what I want to do is demonstrate why this is so helpful helpful, and it is incredibly helpful because okay, we could use this to find the moments of the Poisson distribution, but that's not the actual reason that this is so helpful. Let's have a look at another reason. The other point of moment generating functions, you might recall from the introduction to moment generating functions video, is that if you add two random variables together which are independent, then their moment generating functions just multiply, which is very, very nice. So if we have two random variables defined on some abstract probability space over here, so let's say we have a random variable x and we have another random variable, let's say y, oh well, that's confusing. We're now totally different to the y up here, basically. We've just got two random variables here, and x is Poissonly distributed with some parameter lambda, so it's going to map all of these outcomes onto onto the positive integers 0, 1, 2, 3, etc. And y is also Poissonly distributed. Y is also Poissonly distributed with some parameter mu, and it's going to map all of these outcomes here onto 0, 1, 2, 3, all the positive integers as well. Okay, and they are independent. X and y are independent. Then we might like to ask, we could construct the random variable x plus y, which is just going to map any outcome s in here. So if we have some outcome s, it's being mapped onto some real number by x, so it goes to x of s, and it's also being mapped onto some real number by y, so it goes to y of s. So we're just going to define x plus y of s to be x of s plus y of s, so that's a new random variable. And what we'd like to know is how is that distributed, and that is a very important question which we're going to come on to much later, called the convolution, basically. And it's a difficult question if you just take it like that, but in this case, if x and y are independent, it's extremely easy, because if we take the moment generating function of this new random variable x plus y, then if we take its moment generating function x plus y as a function of t, then it's equal to the expected value of e to the t times x plus y. But this is just equal to the expected value of e to the t of x times the expected value of e to the t of y. Now, if these two random variables, e to the t of x and e to the t of y, are independent, then this splits up, and if x and y are independent, then it implies that the expected value of t of x and the expected value of t of y are also independent, because if x does not affect the outcome of y, then how can the expected value of t of x affect the expected value of t of y? So it splits into the expected value of e to the t of x times the expected value of e to the t of y, which is just equal to the moment generating function of x times of t times the moment generating function of y as a function of t. But we know what the moment generating function of a Poisson distribution is. It's equal to e to the lambda e to the t minus 1. Is that correct? Where did we calculate it? We calculated it back here. Yes, e to the lambda e to the t minus 1. Yes, that's correct. So for y, which was also a Poisson distribution, so that's if x is a Poisson distribution with parameter lambda, we said that y was also a Poisson distribution with parameter mu, so its moment generating function, my as a function of t, would equal e to the mu e to the t minus 1. Okay, so that implies that mx plus y as a function of t is equal to these two multiplied together, e to the lambda e to the t minus 1 times e to the mu e to the t minus 1. And now we just combine them together to get e to the lambda plus mu times e to the t minus 1, which is the moment generating function of a Poisson distribution. So this implies that x plus 1 is distributed Poissonly with parameter lambda plus mu, and we did not prove that. We did not prove that if you have a moment generating function, there is a unique distribution with that moment generating function, but you can prove it. It's not trivial in one bit, but you can prove it, and having a moment generating function of that implies that x plus y is indeed distributed Poissonly with lambda plus mu. But this only works if x and y were independent Poisson distributions. And to emphasize the point that it does not work if they are not independent, let's do a counterexample. So So once again, let's take a probability space, so an abstract probability space, and let's define two random variables on it. Let's define the random variable x, which is Poissonly distributed, 0, 1, 2, 3, etc. And let's define another random variable y, which is also Poissonly distributed, but we're going to now make them dependent. Now, that means that y needs to in some way depend on the value of x. So let's make it as dependent as it can possibly be. Let's say that y is going to equal x. So, whatever value you ascribe to an outcome s via the x function, so x will ascribe some value to s, you also ascribe the same value to it via y. Now, if this argument held true, i.e. x and y did not need to be independent for us to do all of this, then it would imply that x plus y was distributed Poissonly with parameter lambda plus mu. Okay, but that cannot possibly be true, because if you take any value s, it's going to be mapped onto, but if by x plus y, this random variable x plus y will map it onto 2 times x of s, where x of s was a positive integer, so non-negative integer. That means that this is going to be an even integer, which means that the only values that x plus y, this random variable x plus y, can take on are the even non-negative integers. That is not the Poisson distribution. The Poisson distribution takes all values between 0, 1, 2, 3. It takes on all values of non-negative integers. It won't. If we look at the PMF of a Poisson distribution with parameter lambda plus mu, it will be lambda plus mu, e to the negative lambda plus mu to the power of x over x factorial. That will not be 0 for odd values. So this is the PMF, that x plus y is equal to some little x. That's the PMF. And basically, we would want, if this were clearly, if x is equal to y, then it's only going to take on even non-negative real numbers, i.e. 0, 2, 3, non-negative integers rather, 0, 2, 4, 6, etc. It's not going to take on 1, 3, 5, etc. But this PMF is just not going to do that. It's not going to, if I put in 3 into there, I'm not going to get 0. So this argument clearly cannot work if the two random variables are dependent.